Hi everyone, this is Surya. Currently, I'm a PhD student at IIT Kanpur. So today we will start a new chapter, Nuclei. We will solve previous year questions of new chapter Nuclei. So first question. So they had given the mass number. They had given the mass number of a helium. So helium is the uh, one element which present in the universe. Helium. Uh, they had given the helium mass number as 4. Okay, helium, He, so its symbol is He. So they have given 4, and that for sulfur we know, for sulfur it is 32. The radius of the sulfur nuclei larger than that of the helium. So they are given the mass numbers. So they are given the mass numbers. So what is they are asking the radius of the sulfur nuclei is larger than that of helium. So what is the relation between the mass number and the radius of any radius of nucleus is proportional to radius of any nucleus is proportional to mass number power 1 by 3 cube root of mass number. So this is the relation. So they are giving the, so suppose helium radius is, so helium radius divided by radius of sulfur is equal to atomic mass number of helium. What is atomic mass number? 4 by 32 whole power 1 by 3. So it will be, so how much it will be? 4, how many times 4 will cancel out? 1 by 8 whole power 1 by 3. So radius of the helium divided by radius of the sulfur. So they are asking the radius of the sulfur is larger than that of, so Rs sulfur divided by R radius of helium is equal to 8 power 1 by 3. So it will be 2. So option D is the right answer. So next question. The nucleus which has a radius of 1/3 of CS 189. So they are asking the radius which is of 1/3 of radius of CS 189. So it will be B. The lithium ion 73 will be is the 1/3 of, the lithium ion will be 3 will be 1/3 of the radius of CS 189. So going to the next question. They have given the half-life period of, half-life of the radium is 1600 years. Now they are asking the fractional sample of radium that would remain after 6400 years. So they are given, third question, they are given the half-life of radium. Okay, half-life of radium is 1600 years. They are asking the fraction of sample radium that would be remain after 6400 years. So you know what is the half-life formula for finding, right? How to find out the half-life formula? By using the half-life formula we can find this. So all of you know the amount of, this is the formula, the amount of any radioactive substance. Okay, here radium is the radioactive substance. Amount of any radioactive substance, amount of any radioactive substance is is remaining after a given time is calculated by n equal to n naught into half whole power T by capital T, right? So they are giving, so what is T? T is the elapsed time, capital T is the half-life of the substance. T is the elapsed time, capital T is the half-life of the substance. Capital T is the half-life of the substance. So they had given the half-life of the substance is 6400 years, right? So capital T, they are given 6400 years. So half-life of the radium is 1600 years, and the fraction of sample radium that would remain after 6400 years they are asking. So capital T is 6. Capital T, their elapsed time is 6400 years they are given. Capital T half-life they are given as 1600 years, right? So capital T by small t, how much it will be? It will be 4. So n by n naught will be half into whole power 6400 divided by 1600. So it will be 1 by 2 whole power 4. So it will be 1 by 16. So option D is the right answer. So next question. The mass density of nucleus varies with a mass number A. So how the mass density is vary? So all of you know the nucleus of radius already in first question we have seen it is so vary according to the mass number as 1 power A power 1 by 3. So R cube is proportional to A. The nucleus of radius R varies with mass number according to this relation. So R cube is proportional to A. So all of you know what is the density? Density will be mass by volume, right? Mass by volume. So already we know the mass is proportional to A, right? Mass number. So already we know mass is proportional to A. So A is proportional to already R cube. And we know the volume is also proportional to R cube. So when there is a ratio of R cube by R cube, they get cancelled and we will get mass by volume as constant. It won't depend upon R. Mass density of nucleus varies as the mass number A. It is a constant. It won't be affected. So option C is the right answer. Going to the next question. The constituents of atomic nuclei are believed to be. So all of you know what is the atomic nuclei. So there will be suppose there is an atom, the electron is revolving around the. So what there will be in nucleus? It will be neutrons and protons. Neutrons and protons will be there. So option A is the right answer. Next question. In the nucleus, next. In the nucleus, sodium 23, the number of protons and the neutrons and electrons they are asking. So this is the Z, number of protons, okay? This is the Z, the number of protons will be, number of protons. And this is the total, this is the mass number. So A is equal to 23, mass number. So number of neutrons will be A minus Z. So mass number minus 23 minus 11. It will be 12. Okay. So number of protons are 11. Number of neutrons are 12. In nucleus, there will be no electrons. In the nucleus, there will be no electrons. Number of electrons are 0. No electrons in the nucleus. So they are asking protons will be 11, neutrons will be 12, and it will be 0. So option A is the right answer. Next question. The nuclei carbon 13(6) and nitrogen 14(7) can be described as isotones, isobars, isotopes of carbon, isotopes of nitrogen. What they can be described as? So because these two atoms have same number of neutrons, how we can say this will? So for carbon, if you see the mass number will be 13, right? And Z, it will be number of protons. So number of neutrons will be 13 minus 6. So total there will be a 7 neutrons. Similarly, for this nitrogen is also 14 minus 7. It will be 7 neutrons. Both are having the same number of neutrons. So when two atoms are having the same number of neutrons, then we will call it as isotones. So next question. Eighth question. The ratio of the radii of the nuclei 13 aluminium 27 and therium Te 125 and 52. So they are asking the ratio of the radii of the nuclei. So already we know R is proportional to mass number whole power 1 by 3. So we will see the what is the mass number for aluminium. For aluminium, mass number will be 27, right? Radius of aluminium is proportional to 27 whole power 1 by 3. Radius of Therium is proportional to 125 whole power 1 by 3. So if you divide aluminum with the other atom, R radius, both atoms ratio divide 27 divided by 125 whole power 1 by 3. So it will be 3 divided by 5. So here there is no 3 by 5, don't worry. It is just 6 by 10. Both are multiplied with both sides. Numerator is multiply the denominator with 2 with same number, then it will be 6. 6 is to 10 is nothing but 3 by 5. So option A is the right answer. So next question. If the nuclear radius of aluminium is 36 Fermi, approximate the nucleus radius of copper. So they are asking if the nuclear radius of aluminium, they are giving us 30.6 Fermi. Then they are asking the radius of copper. So the radius of nucleus is proportional to mass number whole power 1 by 3. This is the main relation, all of you know. So now suppose R is equal to suppose R naught into whole A power 1 by 3. R naught is a constant of proportionality. Okay. Suppose you know the mass number of aluminium. So what is the mass number of aluminium? The mass number of aluminium will be A1. Aluminium will be A1. It will be 27, right? Right? 27. And the mass number of copper will be A2 is equal to 64. So its radius will be R2. Suppose its radius will be R1. Right? So R2 by R1 is equal to R0 by R0 into 64 divided by 27 whole power 1 by 3. So it will be 4 by 3, right? So R1 is the radius of aluminium atom. R2 is the radius of copper. So you know R1 they had given as 3.6 Fermi. So if you substitute R2 is equal to 4 by 3 into 3.6, it will be 4.8. R2 is the radius of copper atom. Okay. So 4.8 Fermi. So option C is the right answer. So when a uranium isotope U is bombarded with a neutron, it generates a krypton, then three neutrons, and what are the other things? So when a uranium isotope is bombarded with a neutron, then what it will generate? When uranium isotope, so there when uranium isotope, there is a uranium isotope they had given, it will be U 92-235 is bombarded with some neutron. It will give 89 krypton and 3 neutrons. So they are saying 3 neutrons. So there will be 3 neutrons. So plus what other things it will generate, they are asking. So in option, there will be energy. It is a nuclear fission reaction. Okay. When uranium is bombarded with neutron, it is a nuclear fission reaction. So what is the, so is a nuclear fission reaction. What is the mass number of this uranium? So total mass number of the left side 235 plus 1, right? Because this one is 1, this is the 235. right? 235 plus 1 is equal to left side is 89 plus we don't know the thing. What is the AX? This thing, extra thing, we don't know what it will release. We will take it as AX plus 3 neutrons. So AX we will solve. It will come as 144. And the atomic number you will solve by balancing these 92 both plus 0 is equal to 36. This one is 36 plus Zx. Zx is the atomic number, we don't know about that atom. So from this Zx we will get as 56. So the mass number 144 and the atomic number 56, which atom it will be? It will be barium. Barium has 144 mass number and 56 atomic number. So this is D is the correct answer. This is how we will solve this problem. Then going to the next question. The energy equivalent to 0.5 gram of a substance. From the from Einstein's mass energy equivalence, we know the relation between from the Einstein mass energy equation, we know the relation between mass and energy, right? Mass and energy equivalence. We know the relation between mass of the substance M and the energy E. What is the relation? E is equal to mc square. So C is the speed of the light, right? So M 0.5 gram. So it will be 0.5 gram means 0.5 into 10 power minus 3 kg. What is C velocity of light? 3 into 10 power 8 meter per second. If you substitute back in the formula, 0.5 into 10 power minus 3 into 3 into 10 power 8 meter per second whole square. So if you substitute, you will get 4.5 into 10 cube joules energy. So next question. Option D is the right answer. The nucleus of a uranium decays and rest into a nuclei of thorium and helium. Then what will happen? The nucleus of uranium decays into thorium and helium. What will happen? The helium nucleus has less momentum than the thorium particle, thorium nucleus. The thorium nucleus has more momentum. Then here they are given that suppose uranium is there, okay? There is a uranium that decays rest into nuclei of thorium and helium. So uranium is decayed into thorium and helium. So what will happen? The helium nucleus has less momentum than the thorium particles. So we will use the energy balance for calculating. So it is an explosion. A body breaks up into two unequal passes. Both parts will have numerically equal momentum, right? So and lighter part will have more velocity. So the momentum conservation will happen here also. So initial momentum equal to final momentum, but the more lighter part will have more velocity and the heavier part will have the lesser velocity. So here the lighter part will be helium, so it will have more velocity. So helium particles will have more kinetic energy than thorium particles. So the conservation of momentum is suppose momentum if I defined as thorium, momentum of thorium is plus, initially there is no helium, right? Both momentum is equal to 0. Initial momentum equal to final momentum. Uranium nucleus is initially at rest, the total momentum is 0 after decay. So what will happen? Momentum of thorium is equal to minus momentum of helium. So both are magnitudely equal, but the sensor will be different, right? So modulus of momentum of thorium is equal to modulus of momentum of helium. So what will happen? The kinetic energy relation and particle momentum. Kinetic energy Ke is equal to P square by 2m, right? So helium will have much lighter, right? So mass of the helium will be much lighter. The kinetic energy of helium will be more than, if momentum remains same, kinetic energy of helium more than kinetic energy of thorium. So option D is the right answer. The helium nucleus has more kinetic energy than thorium nucleus. So next question. The binding energy of a nucleon, lithium, and the helium are given 5.6 million electron volts and 7.06 million electron volts respectively. In the nuclear reaction, lithium with one hydrogen gives one helium and the energy release. Some energy will be released. So what is the energy released? We are asking. So how we will calculate this? So there is a binding energy they had given. Lithium, binding energy of lithium they are given as 5.6 million electron volts, and binding energy of helium they are given as 7.06 million electron volts. So the nuclear reaction of lithium plus hydrogen gives us 4 helium plus some energy. They are asking what is Q here. So how we will find out the Q? So here the energy released, total binding energy is equal to binding energy per nucleon into mass number, right? So how the binding energy will work? Total binding energy will be is equal to binding energy per nucleon into binding energy per nucleon into total mass number. So because total mass number gives number of nucleons, mass number. So the binding energy, so the energy released Q is the difference between total binding energy of products minus reactants. Q is nothing but total binding energy. I am representing B as the binding energy of products minus total binding energy of reactants. So this is how you will find out the Q. So here given binding energy per nucleon of lithium they are given. So total binding energy of the lithium will be total binding energy of the lithium will be 5.6 into 7. It will be 39.2 million electron volt and 1 H1. So this total binding energy is hydrogen nucleus is a proton, single proton. Hydrogen nucleus proton is a single nucleon. So the binding energy will be 0 for this one. There is no binding energy. The products, these are the reactants. These two are the products is helium. So, okay. So the helium has binding energy is equal to helium binding energy will be 2 heliums are there. 2 into 7.06 into 4. It will be 56.48 million electron volts. So the Q is calculated as 56 minus 56.48 minus 39.2 million electron volts. This is the energy released. So what it is, it will be Q is equal to 17.28 million electron volts. So it will be option D is the right answer. So next question. 14th question. If in a nuclear fission, we are asking if in a nuclear fission the masses of fusion nuclei be M1, M2 and the mass of the resultant nuclei M3, then there is a nucleus fission. So what will happen? What will happen if there is a nuclear fusion? The masses of the fusion nuclei will be M1 and M2, and the mass of the resultant nucleus will be M3. So fission will happen, the M1, M2 bombard, and fusion will happen. There will be formation of M3, and there will be a release of energy E, right? That E is the extra mass is there, na? That extra mass went. So definitely M1 plus M2 is greater than M3, because there will be some energy will go in form of this energy. So that energy is nothing but M1 plus M2, the extra mass into C square is nothing but that energy. So option D is the right answer. 15th question. A certain mass of hydrogen is changed to helium by the process of fusion. The mass defect in the fusion reaction is 0.02 0.02866 AMU atomic mass unit. The energy liberated, we are asking. So 1 AMU is nothing but 931 million electron volts. So similarly, the mass defect delta M they are given. So the energy is nothing but energy liberated is nothing but energy is equal to this. That mass defect energy will be equal to 0.068 into 931. So it will be 26.7 million electron volt. So they are giving. But the certain mass of hydrogen changed to helium by process of fusion. The process of fusion will be two hydrogens form the helium, right? Energy liberated due to we are asking the energy liberated due to per AMU they are asking. So total energy liberated will be 26.67 as per million electron volt. So next question. 16th question. How does binding energy nucleon vary with increase in the number of nucleons? How does binding energy per nucleon vary with increasing number of nucleons? So the energy continuously with mass number increases mass number, decreases with mass number. First increase and decrease with the mass number. So usually the binding energy per nucleon with increasing of nucleons, it will be like this. Initially increases and decreases. So option D will be the right answer. So initially it will increase and decrease. First it increase, so the binding energy per nucleon first it will increase and then it decrease, because the binding energy per nucleon is the measure of how tightly the nucleons, protons and neutrons are bound with the nucleus. It varies with number of nucleons. Okay, low mass number light nuclei binding energy per nucleon is increases with increase of mass number, reaching at around the peak around its elements. Okay, these elements are more stable because of their binding energy per nucleon. So high mass number, what will happen? Binding energy per nucleon gradually decreases as mass number increases. This is because of repulsive Coulomb forces between the protons start dominating over the attractive nuclear forces. So that's why. So going to the next question. Here option D is the right answer. So going to the next question, the power obtained in a reactor of uranium-235 disintegration is 1000 kilowatt. The mass decay of U35 per hour. So according to the energy mass relation, E is equal to mc square, m is equal to E by c square. So they are asking the mass decay. dm by dt is equal to 1 by c square into dE by dt. So this is the energy they had given. What is the energy they had given? It will be 1000 kilowatt, right? So it will be 1 by c square into 10 cube into 10 cube watt. So all are in seconds. So 1 by 3 into 10 power 8 meter square into 10 power 6. So it is the dm by dt. It will come in mass per second, right? But we want mass per decay per hour. So there will be conversion factor, right? So you have to do conversion factor, you have to multiply with. So it is coming in seconds. So 1 hour is equal to 60 minutes. 1 minute equals 60 seconds. So 3600 seconds. So the factor 3600 will go in numerator here. Then we will get it in mass decay per hour. So this is the right answer. So if you solve this one, it will be 10 power 8 into 36 divided by 9 into 10 power 16, right? It will be 4 into 10 power minus 8 kg. So 1 kg is 4 into 10 power minus 5 gram. 1 kg is 10 gram. So we can write it as multiply with 10 and 10. It will be 10 power minus 6 gram. So it is microgram. So it will be 40 microgram mass decay will happen per hour of uranium 235 microgram. 40 microgram. So option C is the right answer. Next question. So nucleus of a mass m emits a photon of frequency mu and the nucleus recoils. The recoil energy will be, okay, a nucleus, there is a mass m, a photon of frequency emits a photon. So nucleus emits a photon of frequency mu and nucleus will be recoils. So according to the momentum conservation, m into mass into u, this energy supply energy, the momentum of the photon will be E by C. So it will be h mu by C. Energy will be h mu. So it's the momentum conservation. The energy conservation will be half mu square is equal to, this is the kinetic energy, the recoil energy of half mu square. So from this relation, you know what is U. So you can write it as half m square u square by m. So m square u square is nothing but h square. Mu is nothing but h mu by c. So half 2m into h mu by c whole square, right? So it will be h square mu square by 2mc square. So option B is the right answer. So next question. Fusion reaction takes place at high temperature because, why the fusion reaction takes place at high temperature? Nuclei break at the high temperature pressure, atoms get ionized at high temperature pressure, atoms get kinetic energy is high enough to overcome the Coulomb repulsion between the nuclei. Molecules break at the high temperature. So what is the reason behind this? Why the fusion reaction takes place at high temperature? Because kinetic energy is high enough to overcome the Coulomb repulsion between the nuclei. Why this? The fusion reaction involves, what will happen? Fusion reaction involves combination of two nuclei, right? Two nuclei combination is involved, like hydrogen isotope to form heavier nucleus. So there will be a Coulomb repulsion will be there. Two positive charged nuclei repel each other due to electrostatic Coulomb forces. Okay, there will be a Coulomb. There will be Coulomb, Coulomb repulsion, because two positive charged nuclei repel each other due to electrostatic forces. So high kinetic energy at extremely high temperature, order of million of degrees, the nuclei gain enough kinetic energy to overcome this repulsion, so that come close enough for the strong nuclear force to take over and bind them together. So high temperature is required. So option C is the right answer. Going to the next question. 20th. So two nuclei have mass numbers in the ratio of 1:3. The nuclear density in the ratio of. So two nuclei have the mass numbers. The ratio is 1:3. Okay. So they are asking the density ratio. So because density already we have shown that it is a 1:1 ratio. So again we will do. There will suppose two nuclei. M1 mass is volume is V1 divided by second is M2 divided by V2. So it will be M1 divided by M2 to V2 divided by V1, right? So the mass numbers are in the ratio of 1/3, right? And volume is 4/3 by R2 cube divided by 4/3 by R1 cube, right? So 1/3 R2 by R1 whole cube. Already we know mass. So R is proportional to mass number whole power 1/3, right? Capital R is. So R2 by R1 cube will be M2 by M1. So M1 by M2 already we defined as 1/3. So M2 by M1 will be 3. So R2 by R1 would be 3. So 1/3 into 3/1. It will be 1:1. So option D is the right answer. So next question. The mass of lithium nucleus is given as 0.042 U, less than the sum of the masses of all of its nucleons. The binding energy per nucleon is given. Then so binding energy per nucleon is, so they are given the mass of the lithium nucleus is 0.042 atomic mass unit. The sum of the masses of all nucleons is the mass of the nucleus is less than the sum of masses of all nucleons. The binding energy is given by 0.042 into 1 AM is nothing but 931. It will be 42 million electron volt. The number of nucleons will be 7, right? Number of nucleons will be 7. So binding energy per nucleon will be 42 divided by 7. So it is 6 million electron volts. So it will be around 5.6 we can approximate. So option B is the right answer. Next question. The binding energy per nucleon of helium and the deuterium and the helium are 1.1 and 7.0 respectively. When two deuterium nuclei fuse to form a helium nucleus, energy released in the fusion they are asking. So they are given the binding energy of the nucleon, okay, of deuterium, okay. Binding energy of the deuterium I am taking as capital D is given as 1.1 million electron volt, and helium binding energy of helium will be is 7.0 million electron volt per nucleon. This is the energy per nucleon. So number of nucleons in deuterium. Number of nucleons in deuterium will be deuterium will be 2, right? And number of nucleons in helium will be equal to 4. So binding energy of 2 deuterium nucleum initial is equal to 2 into PED into 2, because 2 is the number of nucleons. So it will be 4 into 1.1. It will be 4.4 million electron volt. This is the total binding energy initial, 2 deuterium nuclei. So total binding energy final will be 4 into energy of helium. So it will be 7 into 4. It will be 28 electron volt. So total energy released will be the difference between them, right? So E released equal to BE final minus BE initial. So it is equal to 28 million electron volt minus 4.4 million electron volt. So it will be 23.6 million electron volt. So option B is the right answer. So next question. If M, A comma Z, MP and Mn denote the masses of the nucleus A, Z, X, Z, proton and neutron respectively in units, 1 U is equal to 931.5 million electron volts per second. This is the energy. What is the BE? Binding energy represent the BE represent the bonding energy in million electron volts. So the mass defect will be, so according to the mass defect will be Z mass number into MP. MP denotes the masses of the nucleus. Okay, nucleus Z, proton and neutron. Okay, proton Z into mass of the proton plus A minus Z will be nucleon's mass minus total mass AZ is equal to mass defect. Mass defect is equal to, we can write it as BE by C square is equal to Z into MP plus A minus Z into Mn minus M of A comma Z. So if we take this one right side and this one as right side as left one, so option E is the right answer. So it is the right equation. Option E is the right answer. So next question. A nucleus has mass represented by MAZ if MP and Mn denote the mass of proton and neutron respectively. BE the binding energy in million electron volts. So what is the correct relation? So here the difference, actually there is a difference in mass of nucleus and its constitutions, that is constituents. It is called the delta M, mass defect, we will call as mass defect. So the delta M will be nothing but Z into mass of protons and A minus Z will be the number of nucleons into Mn, the total mass, is subtracted from initial mass capital M. This will be the mass defect. And the binding energy will be, binding energy BE will be nothing but delta M into C square, mass energy equivalence. So the delta M, if you substitute here, it will be that part into C square. So option A is the right answer according to this. Next question. The binding energy of deuteron is 2.2 million electron volts. That of the helium is 28 million electron volts. If the two neutrons fuse to form a one helium, then the energy of release is the binding energy of the neutron is 2.2 million electron volts. Okay, and helium given as 28 million electron volts. The total binding energy initial will be initial two nuclei will be. So initially there is two neutrons, right? So initial there will be PE binding energy of initial will be 2 into. So each neutron has two nucleons, protons plus neutrons. So 2 into 2.2 million electron volts. So it will be 4.4 million electron volt. So total binding energy of final nucleus helium 4 will be total binding energy VE final will be 28 million electron volts. So the energy released will be 28 minus 4.4. The energy released in fusion process is between the binding energy of initial and initial binding energy. It will be 28 minus 4.4 million electron volts. It will be 23.6 million electron volts. So deuterium convert into helium. Energy released will be binding energy, the energy released on the formation of nucleus. It will be 23.6 million electron volts. So next question. In the reaction, H2 and H3 gives the helium and one neutron. The binding energy of H2 and H3 and helium are respectively A, B, C in million electron volts. Then the energy of million electron volts released. So here they are given H2, 1 and H3 having the energies A and B amount of energies for the nucleons to be separated. Okay, then helium releases C amount of energy. C amount of energy in its formation. In an assembling the nucleons as nucleus. In assembling the nucleons as nucleus. So the energy released will be C minus of A plus B. So C minus A minus B. So energy, this is the energy released. So option C is the right answer. Next question. In any fission process, the ratio of mass of fission products and mass of parent nucleus. So fission matlab combining. Fission process matlab the energy, actually they are separating out. Binding energy per nucleon for fission products is higher to relative to the binding energy per nucleon for parent nucleus. So more masses are lost. Obtained kinetic energy as the obtained kinetic of the fission process. So the given ratio will be less than 1. So in fission process, the mass of fission products divided by the mass of parent nucleus is less than 1, greater than 1, or the same they are asking. Depends on the mass of the parent nucleus. So actually what will happen in fission process? Heavy nucleus such as uranium and plutonium splits into two and more nuclei. In fission process, heavy nucleus splits into splits into two or more smaller heavy splits into smaller ones, right? So mass of the fission products are less than the mass of parent nucleus because some energy will get released in E is equal to delta mc square, right? So when you divide the mass of the missing mass will be going into the converted energy. So the mass of the products is less than mass of the parent nucleus. So mass of the fission products is less than mass of the parent nucleus. So then will be the ratio of both will be less than 1. So option C is the right answer. So next question. Fission nuclei is possible because of binding energy per nucleon in the atom. So it will be decreased with the mass number at high mass numbers. Okay. They are asking the fission nuclei is possible because the binding energy per nucleon in the will be. So actually what will happen in fission nuclei of the possible because of binding energy per nucleon in the. So it will be a decrease with mass number at high mass numbers. So fission of a heavy nuclei usually plutonium or uranium is possible due to the binding energy per nucleon behavior. For lighter nuclei, lower mass numbers, the binding energy per nucleon increases with the mass. Already we have seen, right? Binding energy per nucleon, it will go, it will decrease again. Decreases with the mass number at higher mass number. So at high mass number, it will decrease with the mass numbers. So option D is the right answer. So next question. In nuclear fusion process, the masses fusing of nuclei M1, M2, and the mass of resultant nucleus is M3. So what is the correct relation between them? So fusion means combining, right? They will be combining. So M3 should be. So what will happen in nuclear fusion process? Two nuclei M1 and M2 combine to form a heavier nucleus M3. So there will be a resulting. So the mass of resulting nucleus is less than the total mass of 2. M3 should be less than M1 plus M2. So there will be delta M. It is nothing but M1 plus M2 minus M3. So that will come as the energy released is equal to delta M C square. So option D is the right answer. There will be mass defect that will be converted into energy, making the process exothermic. So energy will be released. So next question. MP denotes the mass of proton, Mn denotes the mass of neutron, and the nucleus of binding energy B. And nucleus, the binding energy of B, contains the Z protons and the N neutrons. The mass M and Z of the nucleus is given by C is the velocity of light. So mass of the nucleus is nothing but here. Already we have seen this one. Mass of nucleus is mass of proton plus mass of neutron minus mass defect. Okay. The mass defect is given by the binding energy divided by C square. The delta M mass defect is given by the binding energy by the C square from the energy mass equivalence. The mass of the nucleus will be the mass of proton. Mass of proton will be Z into MP. Mass of neutron will be N into Mn minus mass defect. It is B binding energy B by C square. So it will be option D. So next question. If the nucleus 3 aluminum has a nuclear radius of 3.6 fermi-meter, then another nucleus will have radius of approximately. So radius is already totally proportional to A power atomic mass power 1/3, right? So R is equal to R naught into A power 1/3. So nucleus of aluminum, it will be 27. Aluminum will be R naught into 27 power 1/3. And another nucleus TE, R naught into it atomic mass number will be 125 whole power 1/3, right? So if you take the ratio aluminum divided by tellurium is equal to 27 divided by 125 divided by whole power 1/3. So it will be 3/5. So RTE is equal to 5/3 into R aluminum. So they are given this one, aluminum nuclear radius. It will be 3.6. So 5/3 into 3.6. So it will be 5 into 1.2. It will be 6 FM Fermi meter. So option D is the right answer. So next question. The solar energy is mainly caused due to gravitational contraction, burning of hydrogen, and fission of uranium present in sun, fusion of protons during synthesis of heavy material. So as a result of fusion, enormous amount of heat is liberated, which is main cause of source of solar energy. Because when there is a fusion, there is some plus Q energy coming out. Okay, so that is the enormous heat liberated during the main cause of solar energy. So option D is the right answer. 33. Curie is the unit of. What is the Curie is the unit of? Madam Curie is famous for radioactivity. Curie is the unit of radioactivity. So option C is the right answer. Next question. 34. A radioactive sample half-life is 1 month as the label. Activity is equal to 2 microcuries 181991. What would be activity 2 months later? So they had done with a half-life of 1 month, 2 microcuries. Activity is equal to 2 microcuries. What will be the activity of 2 months later, they are asking. So in 2 half-lives, the activity becomes 1/4. So activity on 1891 will be 2 microcurie. Activity before, so actually activity will be proportional to half-life, inversely proportional to half-life. Okay. In 2 half-lives, 2 months earlier, it will be like given the first half-life is sample of 1 month, right? They are given the first half-life is 1 month. So A is equal to A naught into 1/2 T divided by this is the half-life. So at initial time T naught it will be A naught. T is the elapsed time. So for each month it will be activity 1 month earlier. Activity have been doubled. Okay, 2 microcuries. So 2 into 2 will be 4 curies. So 1619 earlier will be 1 month earlier. 2 months earlier will be, it will be 4 into 2. It will be 8 curies. Present it will be 2 microcuries. So it will be doubled, right? 2 months earlier into 2 into 2. So it will be 8 microcuries 2 months earlier. So option D is the right answer. Next question. The nucleus CD have a 2 successive beta decay is given by. It is given by which one? 6115 PA. So in this beta decay, what will happen? So in this beta decay, a neutron in the nucleus decays into a proton. So what is beta decay means? So a neutron decays into proton, emitting a beta particle, electron, and an antineutrino. This leads to increase in the atomic number by 1, but mass number stays the same. Okay, 2 successive beta decays will increase the atomic number by 2. So option. So what will happen here? Let's analyze this one. 48 there. So it will be 48115 CD undergoes a beta decay. So converting a neutron into proton, it will become initially indium 48116. Okay, atomic number increase from 115 to 116. So newly found indium goes beta decay. Now what will happen? Now the atomic number increases to another one. So atomic number will become 50. It will become SN115. So option D is the right answer. So we completed the nuclear questions, all questions, 35 questions. Thank you. We will continue in next lecture for a new topic. I'm ending here.